All right. The quick synopsis for the ghost lecture that had to happen. Again, I'm not going to take too much time because you guys can watch the video later, and at least like 15 of you already have. We're defining a new concept. It's molarity. It really means the concentration of the strength of something. So if we say how strong is the acid or how concentrated is that salt water, what we really mean is molarity. It's defined as moles of solute, or the thing being dissolved, per liter of total solution. And it's usually written something like this: 2 big M HCl, that'll read 2 molar HCl, which means its molarity is 2 moles per 1 liter. Eventually we get rid of the 1. I went through a couple of calculations about how you can do, say you got 20 grams of sodium hydroxide dissolved in a ½ liter. How strong is it? And of course, what does that mean in molarity? So you can just take the grams to moles, divide by your volume, and you'll figure out the molarity of a solution. Basically, just stoichiometry like we would normally do. We're just doing it from a different beginning and end points. Again, I did another calculation, and then I did this solution stoichiometry, where, as I said to you guys before, our calculations are always something to mole to mole to something. In this case, we're going to see that it was something, molarity to mole to mole to molarity, and molarity to mole to mass. And you'll notice, and I'll keep doing this when we do more problems, I keep breaking out the information so that you guys can follow along. Plenty of these to do in your lab and your homeworks, but just briefly, going from a molarity of magnesium bromide to a molarity of silver nitrate. Hopefully you guys can see that if I take my volume times the molarity right here, I'll end up with moles. And so I'm going from molarity to mole, do the molar ratio, and then take the moles divided by the other volume to get a molarity. Again, I don't want to take a lot of time here because I don't want to redo my lecture. If you have seen it, you have questions, stick around afterward and I'll answer them. Watch the video if you have questions. I will have office hours, not tomorrow. I'm in meetings from 8 to 4, actually 8 to 5. But Friday morning, I will pop on at like 8:30 until about 11:30 to just have you guys randomly pop through with more questions. I can also try to do some sort of one-on-one Zooms if I can squeeze them in, if you guys send me an email. So the other one, I went from molarity to mass, and we'll do a few more of those too. I talked about dilution, watering it down. Essentially, that's going from one concentration here to another. Really simple math. So I only did one example there. It really is just divide something out. I talked about acids and bases. We know acids because they're going to start with H. That's from our nomenclature section. But the base was not necessarily defined yet, although you should have maybe had an intuition there that if acids are giving you H's, and at the end you're making water, then the base must give you the OH. I gave you guys some idea of common acids and their properties. They're sour or tart. Common bases, they're slippery and bitter. And low pHs are acids, high pHs are bases, with 7 being neutral. Many of you had this at least somewhere in the back of your brain, probably. I mentioned 1, 2, or 3 H's coming off for the monodiene triprotic. Some people use these verbiages, so you wanted to just be aware of them. There's no such thing for the bases necessarily. And again, as I said in the last video, we know a lot about acids. We like acids. We ingest acids. We eat them. We don't like bases. So that's why you'll see very few examples with bases. I said that strong acids will give you all of their H pluses. There's only 4 of them for this class: hydrochloric, sulfuric, nitric, and perchloric. Everything else is a weak acid. And how do you know? You just ask yourself, would you eat it? So here we have acetic, of course we eat vinegar. Phosphoric, that's in our soda cans and our pickling solutions. citric acid, that's vitamin C. Strong acids give all their H's, strong bases give all their OH's. And if not sodium and potassium hydroxide, it's going to be a weak base. At the end of that lecture, I also said, for all of those things that I've been writing up here that don't appear to be bases, say sodium hydrogen carbonate or ammonia, because you don't see an OH in there, these other two guys got together and came up with another definition where they just ask, is somebody donating the H plus and is somebody accepting it? Even if it's not making water, if it accepts it, we're calling it a base. And I started out with an easy one here of hydrochloric acid and sodium hydroxide. The base, we can clearly see an H going to an OH to make water. But less obvious here is ammonia being a base. And here's where hydrochloric acid, clearly the acid is going to donate the H to the NH3 to make NH4 plus. That means that ammonia has become a base. Now, at the risk of opening too much of a Pandora's box, I know that was fast, but any like burning questions on that, especially if you have watched the video and you had a question?
No, it's all pretty straightforward.
Okay. So I did say at the end of that lecture that I would basically start again with the Bronsted-Lowry and introduce something here real quick before we go into actual neutralization problems and calculating pHs. I wanted to start with something called the amphiprotics. And I'm going to start to slow down here. Amphiprotic. If we think about it, we actually could derive what that means. Amphi, where have we heard that before?
Amphibian.
Yeah, amphibian. And that means both land and water. So that means it can do both. So here we have the word both, and we have protic, so proton. Really what this is when a compound can either donate or accept the H plus depending on conditions. Now there's plenty of compounds out there that will do this. They can either act as the acid, donating, or they can act as the base by accepting, depending upon the conditions they're in. I'm going to write down a couple of equations here. So I have HCl plus NaHCO3. This will make NaCl and H2CO3, which could be H2O and CO2 if you really wanted. I'm also going to write down NaOH plus NaHCO3 will go to make Na2CO3 and water. Now here I have two equations, both of which have sodium hydrogen carbonate, baking soda, but in two very different environments, two different conditions. Hopefully, on the top one, if I ask you which one of these is the acid, you will tell me.
Hydrochloric acid.
Very good. That is clearly the acid here, right? Hydrochloric acid. That's because this H is going to be donated to the HCO3 to make H2CO3. So this is the acid because it donated. And that means that this guy is the base because it accepted. The baking soda is the base. So now, actually, let's take a look at the bottom one. Here, it may be a little less intuitive, but check this out. This H is going to be donated to the OH to make water, leaving on the back end Na2CO3. In this case, that means that that sodium hydrogen carbonate happens to be the acid because it donated the proton, which means sodium hydroxide, which we know is the base, just because it's also a base because it accepted. Now, amphiprotic, when the compound can either donate or accept the proton, the H plus, sodium hydrogen carbonate has that ability, depending on if it's in an acid or a basic solution. Now, in a normal semester, when we would start doing titrations and everything, I would warn you guys that if you spill something, let me know. Because whether you spilled the base that you were going to use for the titration, or you spilled the acid, the thing being titrated, I wouldn't have to think about it. I would walk over to the top of everyone's row there in the lab, and there's a big jug of sodium hydrogen carbonate sitting there, and I just take a handful of that and throw it on it and be done. Because whether it was the acid or the base, I would neutralize it, and then we could just sweep it up. It has the ability to do both. Now, for those who are going into a biology class, these amphiprotics, these are what would set up a buffer system, which is something that resists changes in pH. I'll let your bio class talk to you about that, or come to Chem 121 and we'll talk more. But hopefully it's easy to see here how in one circumstance the HCl, clearly an acid because by its name, would be donating, but a little less obvious here is this guy donating backward to the sodium hydroxide. But hopefully it's intuitive enough to see where that might go. And again, this goes back to those Bronsted-Lowry definitions. Are you donating or accepting? I could have substituted ammonia here for the sodium hydroxide, and the same thing would have happened. I would have just had NH4s over here instead of the sodium carbonates. Okay. Let's talk about neutralization or neutralizing. Neutralization. This is when H plus cancel out OH minus. So neutralizing is taking H's and OH's and canceling them out. Neutralized does not mean neutral though. It does not mean neutral. It only means H plus equaled OH to cancel. Now, I'm not going to delve too more deeply in here, but Melinda can definitely attest that we have spent weeks in Chem 121 proving that once you cancel everything out, the pH is not 7. But I'm going to leave that for a more advanced class. For us, we can just think, okay, we're just canceling out, and that's the biggest take home from this. Now, to talk about this, I'm just going to go ahead and do this by an example, because I think at this point that's the easiest way that we can learn. If it takes 37.55 milliliters of 0.223 molar NaOH to neutralize 25.00 milliliters of acetic acid, How strong is the acid? Okay. So we have a certain volume of sodium hydroxide that was needed to neutralize some vinegar. You wanted to neutralize those out, meaning H's taking care of OH's. Well, first you need to know exactly what's going on. So we need the chemical equation. I'm going to go ahead and give that to you. It's going to be the simple one, HC2H3O2 plus NaOH goes to make sodium acetate plus good old-fashioned water. Where's my chat? Where's my chat button? Somebody say it, actually someone in the chat.
It was just me, don't worry about it. It was just me, don't worry about it.
Okay. Canvas is working now, go figure. Yeah, well, there you go. Okay, now again, I always start us out here with the trivial example, just so we can get our feet wet. So keep in mind, I will show you a little more advanced one here. But this is this one just so happens to be a 1-to-1-to-1 ratio. There's nothing here to bounce. It's already good as we look at it. What I want to do now is to go through, just like I did in the recorded lecture from yesterday, I want us to break down this problem so that we know how to solve it. First things first, this strong word. What am I actually asking for here when I say how strong is the acid?
Molarity.
Molarity. All right, that's what I want. And that means I need moles per liter. That's what I'm looking for. The next thing I want to do is ask myself, if that's what I'm looking for, molarity, moles over liter, is there anything up there that already looks like moles per liter?
Yes.
And what is it?
0.223.
Yeah, this guy right here. I like reminding myself that the big M is moles over liters so that I can see all the pieces there. I also want to remind us, we have this word right here, of. And what does that mean?
Multiplication.
Multiplication. So these two things right here are intricately linked here, that they will be multiplied together. They go together. So keeping all that in mind, let's try to do this problem. So we know that we want to go to the moles of acetic acid. Oops. Let me write that down. Moles of HC2H3O2 per liter of that acetic acid solution. Now, if I have a molarity, I probably want to start with a molarity. So I'm going to start with that 0.223 moles of sodium hydroxide per liter of sodium hydroxide. So I have my starting and my end points there. And as I've said from when we started this with our mass to mole to mole to mass, every single one of these problems that we do from here to the end of the semester is always going to be something to mole to something. So we can actually just do that mantra of saying something to mole to something. And we can get our boxes ready. There are very few exceptions to this 3-box rule. Now, let's do this problem. We need to go from molarity to moles, so we have to get rid of this volume right down here. We have to get rid of it somehow. Is there anything in this problem that looks like the volume of sodium hydroxide that we can use?
Yes.
Yes.
I think you're going to shout out the 3755, aren't you?
Yes.
So we're going to convert that to liters, 0.03755 liters of sodium hydroxide. Now, we don't have to do anything else, so we're just going to be happy about that. And to note that our volumes have canceled, and we are looking now at molarity to moles. Now we have to go from moles of one thing to moles of another. That's pretty standard. We just go to that chemical equation like we did in the mass to mole to mole to mass situation. And so let's see, Canlis, what unit should I put on the bottom? Carissa?
Yeah, sorry, I was trying to unmute myself.
Okay.
On the bottom should go liters of NaOH.
Well, we've already canceled that.
Oh, then moles of NaOH.
Okay, moles of NaOH. And on top, we're going to put,
And then on top,
take a look at where we're going.
we're going to moles of HC2H3O2.
Yes. So we're going to put that up as moles of HC2H3O2. And of course, we're going to our chemical equation there. And I already said it's going to be a 1-to-1 by the balanced equation. So what we've done there is now we've gotten rid of those moles. And look, we've gone from molarity to mole to mole. Now we just have to get to this molarity. So we already have our moles taken care of. We just need the volume. So Destiny, is there anything there that looks like the volume of acetic acid?
The 25.00
So where am I going to put that?
on the top.
On the bottom is correct. Now, why on the bottom? Because my units ask me to have moles over liters, and so I need to make sure those are going to be on the bottom. Don't need to do anything else, so that makes me happy. So I now have my moles per liter, everything calculates out. If you do this, you should end up with 0.335 moles of acetic acid, per liter of acetic acid. Or if you wanted to make that clean, you call it 0.335 molar acetic acid.
Excuse me, sir. What is on the top of the last one?
Oh, this right here?
Yes.
It's a smiley face.
But why are you putting the smiley face there?
Oh, that's right. We haven't talked about that, have we?
No.
Okay. So why the smiley face? That's a good question. I forgot that we haven't had that discussion yet. Okay. Raise your hand if in this thing right here, you freaked out because there was nothing underneath it.
I am
See-
raising my hand.
Thank
I'm
you.
raising my hand too. It won't let me.
Okay, that's fine. Good. So at least you guys are shouting out, and Ming's like, I'll raise my hand. Here's the deal, guys. I'm surprised no one stopped me when they're like, hey, there's a blank spot. Okay. What we are concerned about here, and you know, for the three of you that will go to the book and watch this and do this, you'll find that Chuck likes to flip these two things around because he doesn't like blank spots. He is very OCD in that way. I don't care about blank spots. All I care about are units. Okay, this problem told us to take this 0.223 and that 3755 and multiply them because it said of. I will do that, okay? If I do that, and I just multiply them, as you see right here, if I just multiply these guys right there, all I'm going to do is get rid of my liters and be left with moles. I have now converted molarity to moles. That's all I'm doing. If that's all I have to do, then I don't need anything underneath that calculation. Now, There are people who don't like the blank spots. And so in the past, I've been like, okay, look, guys, I'll just put a 1 there. You know, right? Because anything divided by 1 is just a number. And then somebody raises their hand and goes, where'd the 1 come from? And I'm like, well, I just put it there. And they're like, I don't like that. It makes me uncomfortable. I'm look, I just put it there to make you happy. And they're like, oh, okay. I mean, I don't care if you draw a mushroom there or something. You know, as long as you're like, hey, I don't have to put anything there, I'm okay. You can either leave it blank, you can put a 1, you can put a happy face, you can draw a unicorn for all I care. I'm just filling up blank spaces so you don't freak out.
Is this like a rule? Like, is this something that we can count on as we do these problems, that those 2 positions will likely not have anything there?
Reagan, I hate it when you go for patterns because the answer is no. If you, all right. Man, you guys are gonna do this to me. Look, you don't like it, you don't like the blank spots, but you want something.
No, I don't mind them.
No. Check it out. You could have said the 0.03755 liters. You could have said 0.223 moles per liter. And let me just be careful here. NaOH, NaOH, NaOH. And then I'll do it just like Chuck likes to do in the book. 1 mole of NaOH, 1 mole of the acetic acid, and I'm going to use my own abbreviation there because I don't want to write it out. And then he'll make a calculation. I have no idea what that is. Let me just calculate it real quick. 0.03755 times 0.223. He'll say that's 0.00837 moles of NaOH. And then he'll say 0.00837 moles of NaOH. And then he'll divide that by is 0.02500 liter, or sorry, acetic acid. And he will break this up into 2 problems instead of keeping it all as 1. And the reason why he does that is because everything cancels really nice. You're left with moles, you take the moles divided by liters, and there's no blank spots. No blank spots. I don't like spreading it out because the more numbers that you have to transpose and rewrite and drag somewhere, the more likely you are to do it wrong. But I do want to point out here, Reagan, the reason why I don't like the pattern thing is if I wanted to get rid of the blank spot here, all I had to do was flip-flop these 2 positions. And look, no blank spot. So that's why I'm like, the whole pattern of like, can we always expect a blank there and a blank there? In these types of problems, sure, but I'd rather you not memorize the type of problem to know where a blank spot is. I'd rather you just say, look, I need to go from something to moles. The problem says of me, and we'll get there. Done. Look, I just of'd you. We got there. We have our moles. Then the problem says go from moles to moles. Got it, the equation. And then it says get to molarity. Well, all I need now is moles over liters. Got it. And I don't care if we have anything or nothing on the top of these.
So you know, that's for us, because I was trying to, and now I'm looking back, I was trying to understand in terms of when we first learned mass to mole and mole to mass. And as I'm looking, we have the 1s there. So I get it. Like it really is, even if you do the calculations, whether it's a happy face or whatever, that's how we've learned it. You're just putting it in there, but the ratios, never mind. I guess what I'm trying to say is I understand. It's not anything different than we did in the other conversions.
And you know what? You have just said exactly what I hope that everyone is on the other end going like, oh yeah, this looks exactly like the conversions we've already done. That's what I've been trying to tell you. All of these conversions will look exactly the same. It's just your beginning and ending points may look slightly different. In this case, we went molarities to molarities. In the next one, we're going to go from grams to molarities. So let me do another one, and let's see if that helps. So let's do another one here. How strong is an HCl solution if it takes 25.50 milliliters to neutralize 0.375 grams of sodium carbonate. So I have some sodium carbonate, just as powder. I have to use 25.5 mils of HCl to neutralize it. So how strong was that HCl to begin with? Well, we need this. We need HCl plus Na2CO3. Look like a double replacement, right? So we have the H to the CO3 and then Na2 to the Cl. And again, since sodium carbonate is accepting, that makes this the base. So on the other end, we get H2CO3 plus NaCl, and this guy right here is H2O and CO2. Now, oh, and we should note here then, if we have H2, there should be a 2 there and a 2 there to balance it out. I left H2O and CO2 as H2CO3 for balancing purposes. Now, at this point, we want to ask ourselves, what is the problem asking us? So again, we come up here, strong. How strong is the acid? We're asking for the
Molarity.
moles per liter, the molarity. Yeah. And then, shoot, let's put it down. Let's put it over there. And then let's ask ourselves the other question. So we want to go to moles of HCl per liter of HCl. Is there anything that already looks like the volume of HCl?
Yes, 25.50 milliliters.
Yeah. Okay, so we can clearly get that down here. We're going to use that for the green. Is there anything there that looks like moles?
Yes,
What?
375 grams of Na2CO3.
Absolutely. This guy right here, this grams, remember grams are moles. So what we're going to do is we're going to start with those grams and work our way out. So we're going to start with 0.375 grams of Na2CO3. And we're going to realize this is a mass to mole to mole to molarity problem. Nothing is different here, guys. We're just starting and ending in different spots. Okay. So if this is a mass to mole to mole to molarity, what's our first step?
Define the mass of the NaCO.
It happens to be
Na2CO3.
what? It happens to be 105.99 grams. Where should I put that?
On the bottom.
105.99 grams of sodium carbonate. How many moles is that going to be?
One.
Yeah. 1 mole in the periodic table, 1 mole up there. Okay. Who do we have next here? I'm going to pick on somebody. Emily. What's my next step? Now that I've gotten rid of those grams.
You put the moles of Na2CO3 on the bottom.
And
On top,
on top?
you put moles of HCl.
Okay. Now, how many moles of Na2CO3 should I put on the bottom?
1.
And on top?
You put 2.
Right, because we went to that balanced equation. Okay, oh, hey, look at that. We already have the moles that we want. So all we need now is the volume. And why don't you go ahead and finish it out, Emily? Where should I put that volume?
On top. Or on the bottom. Yeah.
There we go, right? This is why I always put that marker on the far side to remember. Instinctively, we always want to put something on top. How do we read? Left to right and top down, right? So our instinct says put everything on top. That's why I always put the marker out here to the side, be like, okay, I know I need liters. I got to do something with that. Oh, look, they're on the bottom. And so always remind yourself where it is. So it's 25.5. So I'm going to convert that to liters, 0.02550 liters of HCl. And since we're done, does that make you happy, Emily?
Yes.
There we go. So I'm going to put that there just so we don't think that we have to put everything in a box. If you do that calculation, you end up with 0.277 molar HCl. So as we look at this problem, it's no different than our mass to mole to mole to masses or our molarity to mole to mole to molarities. Now it just happens to be a mass to mole to mole to molarity. It's not a problem. All right, let's see if I can do this the old-fashioned hard way. Let's do another one. Let's see if I can kick it up a notch here. How much? 0.315 molar phosphoric acid is needed to neutralize 35.00 milliliters of 0.212 molar calcium hydroxide. Okay. How much is needed? Let's analyze this problem real quick. First things first, we need the equation. So we know we have H3PO4 plus calcium hydroxide. This looks like a double replacement. We know it's a neutralization. We'll end up with Ca3 parentheses PO42 and good old-fashioned water. I won't bore you with the details of balancing, but that's going to be a 2 and a 3 and a 6. Okay, so now we know what is going on. Now we just need to figure out how to solve the problem. Okay, let's look at all of our clues here. Let's see, who haven't I called on yet? Destiny. You ready? Destiny. There we go. All right, this one's for you. When I say how much, what am I asking for? Phosphoric acid, do you think it's a solid, liquid, or gas? Think about any other acid you know. They are all, say liquids.
Oh, this isn't. Oh, yeah, liquid. Okay.
Okay. So if I'm trying to find out how much of a liquid, what type of unit am I probably looking for liquids?
Mm,
Probably
I
looking for
don't
the,
know.
right? So I'm
Liter?
looking for the volume. Huh? So when we're asking for how much here, the couple things you would look at. You want to say like, hey, down here are these solids or liquids? And I guess I should have been a little more clear for you. That aqueous means if we're looking for how much, we are looking for a volume. Okay, look at the other things that we have here. We have of. That of means I'm going to be linking those two together. Now this one is going to get interesting because I'm going to break my little mantra of if I see something, I'm going to start with that. I'm not going to do that. I'm going to start with the way we've been doing things. Now, at the end of this thing, we want milliliters of H3PO4. And I'm going to start with the thing I know everything about, and that's this guy right here, the molarity and the volume of calcium hydroxide. Because if I do this operation, if I do this of meaning times, I will end up with moles and I'll start being able to do the problem. So I'm going to do 0.212 moles of calcium hydroxide per liter of calcium hydroxide. And note that this is a something to mole to mole to something calculation.
Can I ask a quick question?
Yeah.
Okay, so the questions will either be how strong or how much. And if it's how strong, we're looking for moles over liters. Or and if it's how much, we're looking for milliliters?
Or grams. Okay, and the reason why I say that is if you look up here, and I guess I should have also been a little more careful here. Had I asked you this problem backward, meaning if I gave you the strength of the hydrochloric acid and how much, I would have then said, oh, I just put you can't see me put a thumb over my stuff. I would have then said, how much sodium carbonate did I neutralize? So if this problem can go forward, this problem could go backward as well. And so the how much, your clue, and you will be given balanced chemical equations to do this on the exam, your clue is going to come into what is that physical state right there. So in that case, solid, and in this case here, aqueous, meaning a liquid, so we're looking for a volume. Does that help, April?
Yeah.
Okay.
So if it's a solid, we're looking for the grams. If it's a liquid, we're looking for the milliliters.
Yes. Now, again, going back to the problem at hand, we're going to do that of, we're going to multiply. So I'm going to take that 0.035, I'm just going to leave off the zeros, liters of calcium hydroxide. And again, since I don't need to do anything here, I'm done with that calculation because all I needed to do was get rid of my liters. Oops. From there, I need to go from my calcium hydroxide to my phosphoric acid. So I'm going to put my calcium hydroxides on the bottom. And I'm going to put my phosphoric acid on the top. And I'll go to my chemical equation and see if there's 2 phosphorics to the 3 calcium hydroxide. Now at this point, some of you may be going like, well, okay, but how am I going to make moles look like volume? Well, right here. Because remember, there's a moles per liter. There's a moles per volume right here. And so all we have to do is pull that volume out, and we do that by flipping over the molarity to be 0.315 moles of H3PO4. And I'm going to go ahead and say 1,000 milliliters of H3PO4 here. Because that's now going to, oops, wanted that red. That is now going to get rid of my moles and leave me with that milliliters I wanted. And I believe it is 15.70 milliliters of H3PO4. Okay, we went fast through 3 problems. Basically, almost every way that I could do a problem, I have done for you. Do we have any questions before we get to the plug and chug section?
So the reason why you used 1,000 was because you crossed out the mole and the M, and the liter is only 1,000?
No, what I didn't want to have to do, let me just do the last little bit here for you, is I could have said 0.315 moles to 1 liter, and then I would have said 1 liter to make it 1,000 milliliters. I just didn't want to do the last step, because hopefully we're at the stage where we know that 1,000 mils is a liter, and we can just slap it in there.
Okay.
Does that sort of, make sense? I mean, no one has questioned how I just like did my liters from my milliliters. I just moved the decimal on that one. So I took that shortcut in kind of reverse and just put my 1 liter as 1,000 mils so that I can have a number that looks normal. ¿Más preguntas? Because I have 1, 2, 3, 4, 5 more pages to go. Oh yeah. At this point though, they'll be kind of pluggy chuggies.
When will we be tested on this stuff?
Huh?
When's the test date for this?
Monday.
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 Can we have an extension on that?
Do we have a what?
Can we have an extension on that?
Why?
Oh my God, it's too complex.
Oh, you gotta be kidding me. How many more days do I have to push things? That's crazy talk. We're out of time. These problems are no different than we have been doing for like 3 weeks now. We're just starting and ending in a different spot.
Is today's lecture on Monday's test?
Yes. So the pH scale. I want to talk about the pH scale and concentrations of H plus, which we are going to be writing now like this. As we put out before, the pH scale goes from 1 to 14, where we go from our acid to our base, with 7 being neutral. 7 is neutral. When we look at that, there's a reason we have this, this set of numbers, and it's going to come from an equation that I'm just going to put on the board for you here, and just say accept it. If you want to know the ins and outs, come to Chem 121. We'll talk a lot about this. But we need to talk about something called the auto ionization of water. Someone about, looks like you guys are figuring out when to go see Mang for help. Good. The auto-ionization of water is as follows. H2O goes back and forth between being H pluses and OH minuses. And really, this is an H3O plus. If you go to other books, they're being really sticklers. They'll call it an H3O or the hydronium ion. Now, as I write this up on the board, it may be a little interesting to you that for once I'm now putting arrows going both directions on this. It turns out that most reactions will actually go both ways. We don't really talk about it too much in this class about them going both ways, but this is the case, especially with water. And in that, it sets up what we call an equilibrium. Now you can imagine if we go the Wayback Machine to the intermolecular forces, where we talked about the hydrogen bonds that water would like to form. Well, it turns out that when they try to do that, every now and again, they succeed in tearing away one of those H's, making the H3O plus, which we commonly call H plus. Now, there's a problem with that. If the water could do that successfully all the time, we would not have any water. Now, note that as soon as it does this, as soon as it takes this H and this OH, they're going to be sitting right next to each other. So they're immediately going to go right back to make that H2O. Thankfully, now we have liquid water still. Now, with this equilibrium, it sets up something called an equilibrium constant that I'm not going to explain, but we're just going to use. And that is that the Kw is equal to the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. And this brackets like here means concentration. All right. So do you guys just want to talk about all their office hours or something? Real quick, because or it's all in the chat room. It looks like Jordan and April, they're sitting out all the SI sessions for the 3 people. So check those out if you guys are freaking out. Of course, like I said, I'll be here Friday morning and I can set up individual stuff if I can with you guys in the interim as well. Now, this constant right here, this is constant, which means it is infallible. This means if Kw is constant, and it is a number, as you increase the number of hydrogen ions in solution, as those go up, the hydroxide concentration must go down to compensate. They will never go to 0. Okay, they will never reach 0. So the implications of this, well, I should say first, let me talk about what does it mean as one goes up, the other goes down. You can imagine that if you had $100 to give out to your friends, you could either give one friend a $100 bill, or you could give 10 friends $10 bills, or you give 20 friends $5 bills. As the denomination or the number of friends goes up, the denomination goes down. So it's constant, but you can never give out 0 money to somebody because there is a constant amount of it. In the same way, this applies to the H plus and OH minus concentrations. Even in the most acidic solution ever, you will always have some fractional amount of OH minuses sitting in there. And that has to be because all of our solutions, whether they are a base or whether they are an acid, are always sitting in a watery solution. And water will always be doing this somewhere in the background, giving you some amounts of these. Now, it should be noted here, molarities, right? We said those are concentrations. Molarities, concentrations. Automatically tell you the H plus concentration. So this is kind of cool. And this is one of the reasons why we get these molarities in the first place. So consider 0.1 molar HCl. This right here, this 0.1 molar HCl, look at that. There's 0.1 molar of H plus in there. Which is just written as the concentration of H plus is equal to 0.1. Whatever that concentration is, take a look at how many H's are there. You're good to go. What if I have 0.1 molar H2SO4? What is that going to tell you, Yadira? Just because your mic was on. Take a look.
0.005 of H plus.
For every one of those H2SO4s, we have H2SO4. We said that acids give up their H pluses. That means that that's going to give us 2 H pluses and an SO4 2 minus. So for every one of these, we get 2 of the hydrogens. So if my sulfuric acid is 0.1, then my H2 is 0.2. Yadira,
Yes.
does that make sense now?
Yes, because there's 2 H's.
Okay. So Daisy, get your mic ready. If I have 0.015 molar H3PO4, what is my concentration of H plus?
Would be 0.15?
Not 15, because how many H's are there?
3.
So I would have 3 times that to make it 0.45.
Boris, why am I multiplying and not dividing?
Why would you divide?
Well, if I see like there's H3, so 0.015 H3, in my mind to get to just the H plus alone, I would divide.
Reagan asks. No, I know exactly what it is. Because it is a subscript, it is throwing you off. Okay, we have H3PO4 breaking up to give us those 3 H's and a phosphate. Can we agree there?
Yes.
Okay, so watch this. If I have 0.015 moles per liter of H3PO4, and I convert that to moles of H plus, I will see that I have 1 mole of H3PO4 will give me 3 moles of H plus. Which means now I have the moles per liter for the H plus, and that's why it is 3 times.
Yeah. No, when you put it that way, that is helpful.
In fact, let me go ahead and put that in a different color here, just so we can see. So we can see that that's where I'm getting that 3. Now, look at that, 1 page done. So if
So
we
you just
look-
take the number, you just take that number and divide, or and multiply it by however many subscripts there are?
Yeah,
Oh, that's easy.
yeah, it is. Isn't it beautiful? Oh my gosh, it's glorious.
So then are you going to kill me if I ask you about the first formula? I'm still hung up on what KW and U are. Is that
Right.
the formula, that's the constant for autoionization?
Yep, it's called KW. In fact, I'll tell you briefly. Equilibrium constants are called Ks. And so for anything that sets up an equilibrium where it can go both ways, you can even think about your HCO3 that we started this whole day with, right up here, where to go. This HCO3 can go both ways. It sets up an equilibrium, and it can go either way. And it will have its own constant as to how far it wants to go one way or the other, and it is given the value of K.
Okay.
In that case, it would be a Ka because we'd consider HCO3 an acid. At that point, we know it's constant. Water is very specific, so it gets a KW for water. And I don't need you to know anything more beyond that except for that's the number and that's the equation. And we're going to use that equation actually right now because I want to prove to you that you do not have zero hydroxides, even in these acidic solutions. So let's prove that the concentration of OH minus is not zero, even in these acids. So I'm going to take a look at the 0.1 molar HCl. You told me that that meant the H plus is 0.1 because there's only one. Great. So what is OH minus? Right, what is that? We're going to go up to that equation. And we know that the concentration of H plus times the concentration of OH minus is equal to 1 times 10 to the minus 14. We just know that. And in fact, you know what? How's that?
Awesome.
Woohoo!
That's not a U, that's an H. That's an H. That was confusing me. Can you make that look more like an H? Yeah, thank you. Because someone else could get.
Sorry. I know, right? Good.
Thank you.
All right. I told you if my handwriting is sloppy, remember I have good board writing, not good handwriting. All right, so the concentration of OH minus is equal to 1 times 10 to the minus 14 divided by the concentration of H plus. So that's 1 times 10 to the minus 14 divided by 0.1, or 1 times 10 to the minus 13 is the concentration of OH minus. So even in an HCl solution, even in hydrochloric acid and a decently strong hydrochloric acid solution, there are just a little bit of OHs still floating around because water is always going to be doing this to us in the back end. But it's not going to be zero. What if I have 0.0015 molar H2SO4? What is the concentration of OH minus? And H plus, I mean, we'll get them both. So let me just go ahead and get both. What are concentrations of H plus and OH minus? Well, straight away, hopefully you guys can tell me what the H plus concentration is here without any math.
0.0030.
0030.
There you go. Nice. So now all we have to do is get the OH. So we go back to H plus times OH minus is equal to 1 times 10 to the minus 14. So the OH minus is equal to 1 times 10 to the minus 14 divided by my concentration of H plus. Now we can put that in there. 1 times 10 to the minus 14 divided by our nice little 0.0030. And if you do this, you get 3.3 times 10 to the negative 12 is equal to the concentration of OH minus. Like I said, at this point, we're essentially out of concepts, except for one at the end here. And we are into the realm of plug and chug. Before I do one more of those, does anybody have a question about how these plug and chugs are going? Did you want to try that one real quick to make sure you're getting that number?
Would you
That
ask
3,
4 was, or no?
Hold on.
Another element is.
I think you were first.
Oh, sorry.
it's okay. Is that the answer? 3.3 times 10 to the negative 12?
Yeah, I believe so. It's in my
Okay.
notes, but let me make sure. I'm pretty sure that is. Yep, 3 to the negative 12.
Okay, thank you.
Is it just written poorly or?
Yes.
Okay.
Is this when you use the anti-log?
No, not yet.
Okay.
Is that better, Yadira?
I can't see it.
Or
Yes,
not?
that's
Okay.
better now.
Okay. Yeah, sorry, when I get to plug and chug stuff, it's like I just go so fast. Slow me down. Let's do one more just to kick it up just a little bit. Let's do 2.5 times 10 to the minus 4 molar H3PO4. I want the concentration of H plus and the concentration of OH minus. Straight away, you should be able to tell me what is the H plus. I'm going to go with Warnock. What is it?
I don't know, actually.
What's 25 times 3?
Shoot, calculator.
You did not just say the word calculator for that. Somebody save her.
No, 75. I'm sorry. 75.
75. So 2.5 becomes 7.5 times 10 to the minus 4. I know, I'm putting people on the spot. All right, so we have the H plus. Let's just get the OH minus. So again, H plus times the OH minus is equal to 1 times 10 to the minus 14. So the OH minus is equal to 1 times 10 to the minus 14 divided by the H plus.
Mr. Quillen,
Yes.
in the problem, you actually put to the negative 4 power.
Yeah.
Oh, sorry. Never mind. Sorry.
And that's exactly why I kept the negative 4 here. You have to keep that 10 to the negative 4 there. Just because I had 25 times 3 is 75, or 2.5 times 3 is 7.5, you have to keep that 10 to the negative 4 because that's going to be important. Does that make sense?
Yeah, sorry. Thank you.
That's fine. Don't apologize for asking questions. Okay. If you plug those, you should get
1.3 times 10 to the negative 19.
11 is correct.
Oh, oops.
Now, you knew that was, well, because you had a positive 4, I think, on the bottom instead of a negative 4.
So you went 2 decimal places in this equation, but only
It won't matter.
one.
Your test coming on Monday is actually going to be a multiple choice. You'll see the answer.
Oh, okay.
Yeah, I'm going multiple choice here. It takes too much time to download, write, upload, and all that sort of stuff. So I'm going full multiple choice on Monday. I expected a couple of yays out of that.
Hey,
Will we still
Forrest,
have the same amount of time?
No, you're not going to get 2 hours for this. It's going to be an hour exam, and so you'll still have plenty of time to do it. But it's currently only 27 questions, so you got plenty of time. And with some of those being easy conceptual ones, you got plenty of time to do this if you know what you're doing. So
Wait, hang on. So you're gonna give us like the how strong is blah blah blah, the whole balanced equation, and then we have to just do the math and find the answer?
yeah, you'll have the balanced equation, you'll have everything. You just have to do the math.
Cool.
I mean, I told you these last exams are all about just being able to go back to the math and the conversions.
hey, Forrest,
Hey,
can you humor me? And can we do the math on this? I don't know why I'm not getting the right answer.
all right, let me see how you're plugging it into your calculator. Remember to do 1 times 10 to the, meaning hit your EE button.
Oh,
Yeah, we forgot how to do that, didn't we?
no, what I was trying to do is oh my gosh, I'm such a hold on, let me see, I think I
No,
did.
you're not.
Okay, so actually what I was trying to do was I did 1.10 divided by 7.5. I was just reading it wrong. 1 divided by 7.5 is 0.133. I get that.
Okay.
And then 10 to the negative 4 divided by 10 to the negative, 10 to the negative 14. I thought that I would just make that negative 10. Why is it negative 11?
Yeah, you can't do that because 1 divided by 0.75 is 0.133.
Right?
And so if you have 0.133 times 10 to the negative 10, when you move that decimal over, this now becomes 11.
And why did we move it over?
Because that's how you never do this. You always write number point.
We do. Okay, I just want to make sure on that one.
Yeah, that's the proper way of the scientific notation. It's always number point.
Scientific notation, it all goes back to the beginning. Got it. Okay, then I'm.
Yeah, you remember that stuff that you thought you could just forget about? This is where it all comes full
Totally just
circle.
let it fall out of my brain.
Don't let it.
Scientific notation, I'm totally cool. Thank you for doing that.
Not a problem. So how about this? How about I have 0.02, oh, come on. 0.025 molar sodium hydroxide.
Mr. Quinlan?
Oh, my concentration of H plus and concentration of OH minus.
Mr. Quinlan?
Yes.
For the test on Monday, do we have to show our work or just the multiple
No,
choice?
you're clicking. You're just clicking buttons.
Okay, thank you.
Yeah, clicking buttons. All right. But since you're there, Mass, what does this problem tell you? What numbers can we get immediately?
The H pluses.
Where do you see H pluses?
Oh,
Yeah,
sorry.
The OH.
Right. And what is the OH minus here?
don't you, is it 1 times 10 to the negative 14th, or is it 0.025?
0.025.
So,
Just like with the acid, the bases will tell you everything you need to know.
oh,
right?
so when do we use the 1 point?
Oh, we're going to do that right now. Because unlike up here where we had H's and went to OH's, in fact, maybe I should, since I was doing green for them, how about I just do this and make it green? So now we have the OH's. We now have to get the H's.
Got it.
So it's
Oh, so
basically,
that's why we use that 1 times 10 to the negative 14th.
yeah,
Oh, okay, but then it would just be flipped, right? Like it would.
yes, absolutely.
Okay.
So no matter which one you're given, you're always going to have the other one be the 1 to the times 10 to the negative 14.
Yes.
Okay, because I was under the impression that OH is always the 1 times 10 to the negative 14th.
No, in fact, it's not the OH that was 1 times 10 to the negative 14. It was this whole thing right here is to the negative 14.
Oh, so it's like vice versa. It can be either or.
Yes.
Okay.
Forrest, I'm gone. I did this like a million times on this calculator though, and it's still coming out 19.
You did not hit negative 4. You did not hit negative 4.
I did. I promise. I did it over and over and over doing it negative 4.
Hold on. All right, can you guys see this?
Yes.
Okay.
No. See what?
Okay, you can't see it. Hold on. Stop sharing.
Mr. Quillen, I think she's putting minus, like the subtract 4,
Yeah, so
but she's not putting the parentheses minus 4.
You need to do 1 times 10 to the negative 14 divided by 7.5 times 10 to the negative 4. I believe that's when we're doing. Oh, hey, I didn't have my screen on, but are you hitting that negative there or are you hitting the minus sign?
Negative sign. I'm not stupid.
I didn't say you were. Do you have one of these?
Remember your parentheses too.
You could parentheses each of them before you do the dividing thing. How about we work on it after class? I'll look at what you're punching and we'll figure it out.
Okay.
Okay. So stop that. Reshare. Get rid of my OneNote. Okay, so now we're back to there. Let me get my participant list up here so I know where to stop writing. All right, so back here it's 1 times 10 to the negative 14. We're now going to divide that by that 0.025. And we'll see that even in a basic solution, we still have 4.0 times 10 to the negative 13 as my concentration of H plus. So even in a basic solution, we still have some H pluses floating around. And just to hammer down the math one last time, 0.001 molar calcium hydroxide. I want concentration of H plus and the concentration of OH minus. And I'm going to pick on Stewart. What quantity do we already know?
0.001.
Two.
Oh, yes, you're right.
Yeah, always be conscious of that. That's the reason why I wanted to hammer this home one last time. So yeah, we have 2 hydroxides there, so we multiply it by 2. So now, once again, very boringly, concentration of H plus times the concentration of OH minus is equal to 1 times 10 to the minus 14. So our concentration of H plus is equal to 1 times 10 to the minus 14 divided by the concentration of OH minus, which is 1 times 10 to the minus 14 divided by 0.002, which will give me 5 times 10 to the minus 12 is my concentration of H plus. So hopefully all of that is just a plug and chug. Unless we're having calculator problems, then I'll fix those later. So, oh my gosh, we just spent a long time getting these concentrations. So why? Why find all these concentrations of H pluses and concentrations of OH minuses? Because that has everything to do with pH. pH is equal to negative log of the concentration of H plus. That P actually stands for negative log of. Hearing no applause, maybe I should just, oh, was that a yay? Okay.
Yay.
All right, then I'll let you keep it. Nice, Emily did applauding. All right, so what we want to do is if we look at the concentration of H pluses, we can actually now determine the pH that thing would be. So let's do it for all of our former examples. Can I write that better? Ugh. Do it for all our former examples. This way we don't have to do calculations over and over and over. So we had our 0.1 molar HCl. You told me that the concentration of H plus was equal to 0.1. Nothing surprising there, we just did that calculation. So this means that the pH is equal to negative log of 0.1. Now, hopefully, if you plug that into your calculator, you will get 1. Go ahead and try that real quick and see if you got it. I should say, if you didn't, let me know. We had 0.0015 molar H2SO4. You told me the concentration of H plus, 0.0030. Plug and chug, pH equals negative log of 0.0030, or pH is equal to 2.52. Notice that our pH is rising. It is rising up because we have less and less H pluses in there. We have fewer in there to do the job, so we're not going to be quite as acidic. We had, we had 2.5 times 10 to the negative 4 molar H3PO4. You told me that the H plus concentration was equal to 7.5 times 10 to the negative 4. And this is the one where I'm going to pause to let you guys try this to make sure we're doing it right. pH is equal to negative log of 7.5 times 10 to the negative 4 and hopefully you will get a pH equal to 3.12.
I got it.
Mostly, did anybody not get it who is attempting it? All right, hearing nothing.
I got it.
Yay. Let's do those basic ones, okay? So that 0.025 molar NaOH, you told me that the concentration of H plus was 4 times 10 to the negative 13. pH equals negative log of 4 times 10 to the negative 13. That should give us a nice basic pH of 12.4. Now that makes sense. Big numbers are for bases. Bases are big numbers. This is sodium hydroxide. Our pH should be somewhere in the big numbers, and 12.4 is big. So when you have any sort of solution, whether it's an acid or a base, you can calculate the H plus concentrations, the OH concentrations, and then that will lead you to be able to do the pH of any solution. So you can tell me what is the pH of that solution. If you can go one way, you can go the other. And what do I mean by that? Is we can get H pluses from pH. And that is just taking that pH equals negative log of the H plus and inverting it with the anti-log. And so that would just be that the concentration of H plus is equal to 10 to the negative pH. Say it again, Sume.
Screw up a little bit. I want to see the.
Is that good?
Yes, thank you.
Okay.
Yay.
Thank you. Now, I'm just going to do 3 quick examples. I want to point out that this is the anti-log button. So it's the second function to your log button. And this is truly a plug and chug. So we're going to look at pH is equal to 2.7. We'll look at pH is equal to 8.2. And we'll look at pH is equal to 13.3. The concentration of H plus is equal to 10 to the negative 2.7, or it is 10 to the negative 8.2, or it is 10 to the negative 13.3. If you do these, you should get 1.995 times 10 to the negative 3. You should get 6.31 times 10 to the negative 9, and 5.01 times 10 to the negative 14. Those are just a punch it on your calculator and go. There's really nothing to tell you more about that, except to look at what it means. at our low pHs of 2.7, we expect to have a lot of H pluses floating around in solution. It's an acid. By the time we get to 13.3, we are a base. We should have very little H pluses floating around. And hopefully you can see that 1.995 to the -3 is much bigger than 5 to the -14. We watch as we become more basic, our concentration of H pluses drop off accordingly. Okay.
Okay.
You're not getting it, April?
Well, when I put in the 10 to the -8.2, I get, oh wait, never mind. Just joking. I got that.
You're just joking with me? Okay.
Just kidding. Ha ha ha.
Okay. All right, last thing, guys, and then I'll answer some questions, and then we'll call it. I will also be around this afternoon from 1 to 2 to answer some questions about this lecture and the other lecture as well. I have a meeting from, I think, 2 to 3, and then I'll pop back on again as soon as I can after that meeting. Hopefully it doesn't go very long, but I plan to be just hanging out all afternoon to answer questions. Last thing I want to talk about, though, is the electrolytes. Now, when I say electrolytes, what's the first thing you probably think about?
Gatorade.
Gatorade. Yeah, except for Gatorade, just sugar water. It's not entirely true. There are some electrolytes in them. An electrolyte, by definition, is a solution containing ions. Now, electrolytes are there because you need ions to transport charge current through water. Now, just for definitions, electricity is electrons, current is from the ions. Now, a lot of people might remember the old 80s horror flicks where somebody's taking a bath in a bathtub and the bad guy comes by with the toaster and drops it in and electrocutes them. And they're like, oh my gosh, all the electricity went through them. It actually wasn't the electricity, but it was actually the movement of that little Epsom salt bath that they were soaking in. It was the movement of that carrying the current through them that killed them. Now, I'm going to draw something here just to try to illustrate what I'm talking about. If you want to know more, come to Chem 121. If I had myself a nice little watery solution here, and on one part here, I put a couple of electrodes, and I'm going to connect them with a nice little voltmeter. Let's say that I had some sodium ions and some chloride ions floating around. Okay, good old salty water. Okay. If I suddenly charge these things up to be positives and negatives, so I've basically taken 2 live electrical wires, stuck them in that water. What do you think is going to happen to those ions? Stuart, are you still here? Oh, he's not. So who am I going to do? Yadira, or no, Sanchez. What do you think is going to happen? You can go ahead and say, I don't know if you really want. I'm going to assume you say, I don't know.
They're gonna attract
The
Ooh, say it. Someone's saying it. Do it.
the negatives are going to go to the positives are going to go towards the negatives.
Yeah, why wouldn't they, right? So right now, they're swimming around in solutions. They're like, we could stay together, but we have this water cage around us keeping us company. Remember that ion dipole interactions. But all of a sudden, you put some bright, shiny positives and negatives there. And what's going to happen is those negatives are going to rush over there and try to match up. And the positives are going to rush to the negative one, doing the same. And it's this transport of the ions through the liquid medium that is carrying the current. Now, if you don't have ions, you can't carry current. And if this were a normal semester, I would actually take a live open circuit and I would stick my hand in deionized water, no ions, and I'd plug that thing in and I'd keep my hand in there for as long as I wanted. I would not be electrocuted because there's nothing to transport that charge. There's no movement of anything. I'm safe. Now, put some salt water in there. I ain't sticking my finger in there. It's not going to happen because I wouldn't want that shock of the movement of those ions through there to mess with me. So what does this mean? In order to be a good electrolyte, oops. You must give your ions. You must give up your ions in solution. All right, so if I toss you into that water, if you're going to be a good electrolyte for me, you're going to have to break up and give me those ions. Okay? Now, what might be a good, strong electrolyte?
salt.
Yeah, right? I've already been saying that. So salt, good old-fashioned NaCl, that would be a good one. So I would say soluble salts. So it doesn't have to be NaCl. It could be KCl. It could be iron bromide. It doesn't matter. As long as it's soluble, that means it will break apart. Who else might break apart?
The strong acids.
Yeah, strong acids. We said the whole point of a strong acid was you give me all of your ions, which means, right, the next one you're going to tell me is the strong bases, because those are going to break apart. So if not A, then B. What is a weak electrolyte? Well, if not strong acid, then weak acid. If not strong base, then weak base. And if not soluble, you go with insoluble salt. Or a non-ionic solid, right? So what's a non-ionic solid? Something like sugar. So I could actually take sugar water, as long as it's deionized water. I could dissolve sugar in there, and I still would not electrocute myself because there's no ions to actually transport the charge. So then, this is what it sort of comes down to. All things equal, all things being equal, who is best electrolyte? Going with our definitions of which is going to be the best. I'm going to say I have HCl, NaCl, H2SO4, FeCl3 and CaBr2. Now, every one of these is soluble. So which one of these do you think is the best? I'm going to go with
H2SO4.
Okay, so April says H2SO4. Does anybody else agree, disagree? Just going to hang out? Okay.
I agree with that as well.
All right, so we have a couple of here's, okay.
So
That's the one. Now, why? Why is that the one? If we take a look, this HCl breaks up into an H plus and a Cl minus. 2 ions to do the work. NaCl breaks up into Na pluses and Cl minuses. Again, 2 ions. H2SO4, this is pretty good. It's used in your car batteries because it's a great electrolyte. It's 2 H pluses and an SO4 2 minus. Well, now we have 3 ions looking pretty good, but oh, here we go. That's going to break up into an Fe3 plus and 3 Cl minuses, 4 ions to do the work. That means you have 4 more hands. And then, of course, this guy is only 3. So this is the reason why I would say that all things being equal, the iron is the one that would be the best. Now, I put best in quotes because depending upon your actual physical situation, you may not want to use that for other reasons. But I do want to point out that just ion for ion, this is what you want to do. You want to look to see who gives the most ions. And that would be your technically best electrolyte. All right. Whew. That was a whirlwind. All right. There's something going on in chat. I don't know, sorry. What's the I don't know, sorry, Yolanda? Oh, you weren't miking me, you were telling me. Oh, that's funny. Sorry. But I read your mind, so I guess that works. And don't be sorry for not knowing. We're all learning here. It's okay. All right. So any burning questions before we all go get some food and come back?
No.
No, everything's pretty straightforward.
I will be sending out an email sometime soon detailing, but basically you guys are going to have a multiple choice test. It's going to be 1 hour long, and the window for taking it will shrink down too accordingly. And I'm doing this because it's just going to make it easier. There's no more cam scanner. There's no more downloading and uploading. We just take the exam and we're done. So we're gonna do this for the rest of the semester. It sucks on my end because it's a lot more prep of writing because I have to come up with a whole bunch of different scenarios. But I think it's going to be easier on you guys to do it this way. So I guess that's it. So I'm gonna stop recording. Ugh.